Hello. Hi guys, good morning. So this question, I don't know what people have seen, made, even the solutions people have made. Like none of them have explained the recursion tree. I was like, and for sure. What I think is his question is harder than Stone Game 1 and Stone Game 3. So I don't know why it is the case, but yeah, let's see this problem. We will see entire recursion tree. Okay, how that example which is given in the problem, it's being made and all that stuff. So before further ado, let's start with the question itself. No overacting this time for sure. I will try. But yeah, Stone Game 2. Alice and Bob continue their game with the piles of stone. For sure, cool. We have a pile arranged in a row. Cool. We have a number of piles arranged in a row, and each pile has a positive number of stones in it. Piles, and each pile have positive number of stones called as the piles of 5. The objective of the game is to end with the most number of stones, which means that person who is starting off, or the person who wants to end the game off with the most number of stones. And the players playing are Alice and Bob, and they play alternatively. Alice starting first with the M as 1. And what is M? M is nothing but, okay, on each player turn, that player can take all the stones in the first X remaining piles. We will see what this X is, but that X is dependent upon M, which is X should be less than equal to 2 into M. We will see what that stuff is, and then if a person takes X as X piles, then I have to say, okay, the next person can take M as what the last person took X. That is the maximum limit of M, or the existing M, if it is. Assume the game continues until all the stones have been taken. So basically, until all the stones are occupied either by Alice or by Bob. And assuming Alice and Bob play optimally, which means that, okay, Alice will start first, so he or she, whatsoever, will try to maximize whatsoever number of stones he can get. If Bob will start first, then he will try to maximize whatsoever number of stones he will get. For sure, Alice is starting first, so he will try to maximize his stones. Sorry, she will try to maximize her stones. And then, as Bob is having a chance, like Bob is having second chance, so he will try, okay, whatsoever he can get maximum so that Alice can get minimum, right? It is how we play optimally. Even if we are losing, we try to lose by minimum margin, which means we will try to make other person profit as minimum as possible. Okay, return the maximum number of stones which Alice can get. So we are only concerned about Alice stones, which means Alice is starting first, so whatsoever she can get, we are concerned with that. For sure, we take the first example. If we have 2, 7, 9, 4, 4, 1, initially M is 1, which means I can take only one stone. I can take only one pile. So one pile, I can just grab this stone. Alice can grab the stone. Now, X was taken as 1. So basically, M is again 1. So for the next person, M is 1, which means he can take from 1 to 2 into M, which is 2 piles. So X, which means the next person, Bob, he can take either one pile or 2 piles. So let's say for optimal game, let's say playing, in this example, I will show, okay, it is given that, okay, X, which means Bob, will take as 2. So Bob will take, because for sure, we can see how this also is happening, but yeah, for sure, Bob will try to take X as 2. Now, X as 2, which means the new M is actually a 2. So basically, the new X would become 1, 2, 4. Right now, for sure, Alice can take 4, so it is more. So Alice will take all of them. Thus, it is how will become that Alice can take these 2 and this 4 and this another 4, which means Alice will get the score of 8 and Bob will get a score of, see, although Alice tried to maximize hers, but still Bob wanted, okay, if I can maximize, I like maximize. If the Bob would have taken only 1, because see, you remember, right? Bob had 2 options, X as 1 or 2. If Bob would have taken 1, then our next X, because see, M would have been 1 only, so next X would have been from 1 to 2, for sure. Then Alice would have taken this 2, 9 and 4. Thus, it is of no chance that, okay, Bob would be getting 7 and 4. But it was in Bob's hand to take either only 7 or both 7 and 9. And it's the Bob chance. So he will try to maximize his. That's the reason Alice would only get 8 plus 2, that is 10. That is the answer. The answer is 10. This example, we will see it very clearly, and by this, we will make the recursion tree and see what is happening in that recursion. Cool. For sure, Alice is starting first. Now M is 1 because we know that okay, in the starting M is 1. Now for sure Alice can only take X as from 1 to 1. X is from 1 to M. M is nothing but 1. So Alice can only take one pile. Alice take one pile. Now the pile remaining is this part. Now it's the chance of Bob. Now for Bob, M is nothing but 1. So the chance he can take as X is from 1 to 2 into M. And M is nothing but 1. So it is up till 2. So X can be either 1 or 2. Which means Bob will try to maximize and see if I take one stone and make Alice take the rest of the decisions. If I take two stones and make Alice take the rest of the decisions, whatever will be maximum out of these two, I will take that. Bob is greedy. Like Bob wants to choose. Okay, like not greedy. Bob is whatsoever. I will give you many options. Whatsoever you give me the best option of, I will take that. Which means Bob will try grabbing only one pile. Bob will try also grabbing two piles. Okay. Then here if I grab one pile, so M is 1. Here if I grab two piles, M is 2. Now for the next chance is of Alice. Now Alice again given the options that okay, she can start from this index. Alice, she can start from this index. M is 1, so X is nothing but from 1 to 2. M is 2, X is nothing but from 1 to 4. Now Alice will try to maximize from here, from this part. 3, 4, 5. Now Alice again, she will say, okay, shall I take one pile or two pile? Because she has option to take one pile or two pile. So Alice will try to take one pile, Alice will try to take two piles and give the rest of the piles, which means the suffix piles, to Bob. And now the Bob will have the chance to actually maximize his number of stones. Now here also the Bob will have chance. Now in this case, when X is from 1 to 4, now X can be 1, 2, 3 or 4, which means Alice can have all options that she can grab either 1, either 2, either 3, or like 4 is not there. And as we can easily see that okay, for sure we have 4 piles. For sure we have 4 piles, which means Alice can grab all of them, all the remaining end. So why she will leave anything for the Bob, right? She will grab all of them as simple as possible. So as soon as the limit exceeded for N, for this part, okay, as soon as it entirely is covering, which means my X is covering entire suffix, so for sure the remaining player will try to take all of them because he will not, because see, all the stones are positives, so for sure grab all of them. Value will only increase, nothing else. So that's the reason value will only increase. Now what happened because of this is, now it is one case, okay, the Alice will get this score and this score, but considering the fact that Bob had a chance, either he can take 2 or maybe he can take 1 and then choose. Then if we just go on again in this, now again Bob had a chance, again M was 1, so again X is from 1 to 2. Again what happened is Bob had a chance, so either he can take 1 or he can take 2. Now remaining part is of Alice. For sure X is here, M is here 1, so X will be from 1 to 2. So remaining part Alice will try to take. So Alice will try to take the whole remaining part. Now for this M is 2, so X is from 1 to 4. But no worries, 1 to 4 still Alice will try to take all the remaining part. Now we will go back and see by this step, Bob score should maximize. By this step, Alice score should maximize. By this step, again Bob's score should maximize. So basically at this step if we go on, because it was the chance of Bob and he wanted to choose that okay, if I choose 1 or 2, thus I am saying from this step, from the last step, Bob needs to maximize. From this step, Alice, because it is the chance of Alice, right? Alice can choose anything. Alice wants to maximize hers. That's the reason at this step, and you will see. Now here is the chance of Bob. Bob, let's say he take as 2 only. Now the remaining chance of Alice. Alice has again 2 options, 3 or 3, 4. Again the chance of Bob, 3, 4, 5. Now you will see, if Bob wants to win, like Bob wants to maximize, so why you think that Bob will take only 1? For sure, Bob will never take 1, because see, Bob had options, either he can take 4 or 5 or only 4. If he take 4, then he know remaining part will for sure Alice will take. I have at least 2 options to take, so let me take 2 options. So he will never take this, right? I'm just showing you how mathematically, how logically you can think of making this recursion and making you think, okay, actually how you can find the answer, because many people were confused how this recursion tree was being built, because actually to make this recursion tree, it's actually hard. And still, how this answer 104 is coming. Now, I'm just backtracking you back to the above part. Now, for sure, you got to know that Bob will try to take these two, so remaining part will be of Alice. Now, this whole part is set. Okay, it is good. Now, we are good that, okay, 4 and 5 will be of Bob, and 100 is of Alice. Now, if we just go up, this whole part is set, this whole part is set. Now, if we just look at this part, now if Alice had an option, either he can take 3 or either he can take 3, 4. If he had taken 3, 4, if Alice had taken, when I'm saying he, please, I am mostly concerned about Alice as a guy. Alice can be a girl also, so please forget that part. But yeah, Alice had two options. Either she can take 3 or she can take as a 3, 4. If she had taken 3, 4, then she for sure know that Bob can take 5 and 100, which is much bigger. So Alice will never try to take 3 and 4 both. She will try to take 3, so that Alice, the next person, Bob, he can only take 4 and 5, and then maybe Alice can take 100. It is what Alice is thinking right now at this point. Thus, Alice would not take this. Alice will take this part. Now, okay, we are also very clear with this whole part from 3, 4, 5 that how it is working. Now we again went up. Again we went up. Then we know, okay, this whole part is sorted. Now again Bob had option to take 2 or take a 2 or 3. Again, it's very simple that Bob knows that, okay, if he takes a 2 and 3, then the next chance Alice can take 4 or 4, 5 or 4, 500, which means if the Bob had 2 and 3, then Alice will have 4 options and she would take everything outside. And 100 will also come in. So the Bob right now would be thinking, okay, if I take now, for sure everything would go to Alice. So for sure he will not try to take this part. He will try to take this so that Alice can choose maybe 3 or maybe 3, 4, and not more than that. Maybe in future, maybe it is very small. So maybe that's the reason we are just grabbing for that part. Okay, for every options which Bob is bringing and what Alice is bringing, for every option, okay, the Bob is bringing for 1, for 2. So I'm trying for every possibility of Bob. Okay, cool. What he can bring me? What you can bring me? If I choose X as 1 for the Bob, then rest of the part how it can actually maximize. So everyone, Bob and Alice at every step is trying to maximize their score, and that is the reason I can just take this B, only 2, and 1 is for sure only here. That is the reason you just get this maximum value as 104. Thus you get the score of Alice as 1 plus 3 plus that was 100. Yeah, 104. That is how you got this recursion tree. Right now, it's a simple recursion. At every step you are doing nothing, but at every step you have this M, because see, M will increase on the basis of what was the previous M, right? And what is the current X chosen, and what is the previous M. By this funda, your current M will increase or change. And other option was, okay, the index which is being changed. Okay, for now I is here, then in the next iteration my I will be starting from the index 2, and here you saw the I was starting at the index 3, and it depends upon what the X is being chosen. Because what was your last I? My last I was at this location 2, then because of this X chosen as 1, my I became at this location which is 3, and for X chosen as 2, my I came at this location, that is 4. So basically I have just I index which is being moved like this, and an M variable which is being changed because of what X I choose, and X is nothing but from 1 to 2 into M. Thus I can simply drill down this recursion into my code and actually find my answer, which means initially my M starts as 1, and I also know that my M will go, it is a question part, M will be actually maximum of M or X, and X is nothing but from 1 to M into 2. It is given in the question. So at every index I will just try to take every of those X which is from 1 to 2 into M, and then I will just try, okay, this part of suffix, he can have the sum, which means B for Bob, he can have a suffix sum from I, from this, because if I just have this index I, then the rest of the part is a suffix sum. But considering the fact that Alice will take the next option, which means my function, let's say name it as anything, helper function, anything. So my helper function will actually be a function which maximizes anyone's score. Either it's Bob or of Alice, because everyone want to maximize, right? So either if it's a Bob or Alice, both will try to maximize it. So if I is here, then my helper function will try to maximize the score of next part, which is Alice. But I also know that the next part is starting from, if it has taken only one element, so next part will start from I plus X. So I will try to maximize from I plus X, considering my new M has become maximum of existing M or X. As simple as that, because this helper function will try to maximize the Alice score, and this suffix part will be of from Bob location. By this, I will just try for this particular I here, and also the I is here, but the X is going to change for this particular location, X equal to 2. So I is here, but X is here, which means suffix part will have, here it will have a sum as 2, while here it will have a sum as 5, minus the helper part, it will try to maximize it, which means helper of I location is this part, which is index as 1. So 1 plus, if I choose to choose 2 elements, so I will become plus 2, and maximum of existing M was 2, and new X is actually your 2. So that is how I can actually just replicate what we saw in the recursion tree diagram, just actually replicating that same stuff, because it is the sum, suffix sum, but in that suffix sum I need to subtract the Alice, what Alice can bring off to her. That is what Alice can bring off, and if whatsoever maximize, and ultimately I'll just take the maximum of all the options I have. It is just one option. So all the options between all the X's I just make down, I will just try to maximize that, which means ultimately I have a max answer which will try to maximize this all X's, and it is the existing answer which I have. So I will just try to maximize this whole stuff. I'll show you the code very neatly. But yeah, it is the entire logic of this recursion. And we for sure could see, although in this example you cannot actually see C, but in a sense it's actually very big recursion tree to actually show this in the entire diagram. But we can actually easily see that it's a combination of this index I, which is starting, and also this M. So as this part can easily repeat anywhere, you see by diagram itself, it can repeat anywhere. Maybe it is here, although I could not make that whole diagram, but it can repeat anywhere. Thus, we can also see that, okay, M combination and maybe starting, because you see orange part, blue part, this is okay, starting from this index and current value of M, which means, okay, what all grow, it can grow. By this combination, we can easily see that, okay, it can have a repeating sub problem. Thus, this recursion tree we can memorize and actually get the help of our DP. So for sure, we know that we have two parameters, which is the index, which will actually help us to iterate on this entire piles array, and also the current M, which will actually get varied and help us to find all the X's, because X's is from 2 to M, and X's is, okay, how much piles I can choose at a particular point of time, right? Thus we saw, okay, it can have a repeating sub problem, but I tried to entirely show you the recursion tree which no one has made. If you have seen anyone making it, just comment that person's name or his video or his link, anything you can comment. Leetcode, editorial solution page, anything you can comment if anyone has made this recursion tree for you guys. But yeah, if it is the case, then simply just memorize that part and you are good to go. Now, seeing the code, it's very simple, exactly what we have done. I'll just maximize this. Firstly, a very normal base case, although it will not happen, but still, if piles is empty, just return a 0. As simple as that, no score possible. Now we just do a memoization, because we know we need to memorize. We will also see it later, but still, just remember, okay, we made a memoization DP array, as simple as that. Now, as I showed you, I need to have a suffix sum, because I was concerned about the piles sum, right? I was concerned about the pile sum. I need to find, okay, one option is I just find this sum, entire sum again and again, which will take a O of n operation, for sure. Rather have a suffix sum, then subtract this part, which is because maximum part will be coming from recursion. So rather I have this entire thing compute again and again, or simply have a suffix sum which will compute the sum from here up till end. I have made it entire very dirty. But yeah, from here up till end and from here up till end, and then you can easily subtract your helper function from your suffix sum. As simple as that. I just did. That's the reason I just made a suffix sum. Now I just made a suffix sum. If you don't know, a suffix sum is nothing but if I have an array as 1, 2, 3, 4, 5, I just made a suffix sum from end, which is 5, 9, 12, 14 and 15. Like this, I make a suffix sum from the end. So to actually get, okay, if I just standing at this location, then I can say, okay, from here to here, the sum is nothing but 14. If I'm standing at this location, from here to here, the sum is nothing but 3. The sum is nothing but this 12. That is how the suffix sum works. Cool. Now you know what is suffix sum. I just simply computed that suffix sum the same way I showed you right now. And by this, our firstly, the end index is computed as it is. I just went in from piles of I minus 2 because I plus 1 I am do and I don't want to go over bound. That's the reason I just found the suffix sum entirely at this location. Now I just called my helper function, which will bring out the maximum score for Alice. Now as we go into the Alice function, as we know that we have index and we have an m. Now index, for sure it is going in the piles array, so as soon as it reaches the end I have to return 0 because for sure no score is possible. And also we saw one thing, if I am at the index and I know I can choose my x as from 1 to 2 into m, and I also make sure that, okay, I remember one thing also, at this point of time you saw one thing, when Alice, what was, okay, yeah, at this point of time you remember one thing, right? Alice could take entire x was from 1 to 2 into m, which is 4. So Alice could take entire thing, as simple as that. So if she or he can take entire thing in the end, then for sure he or she will try to take the entire stuff. Thus I just check, okay, if I plus 2 into m, if it is more than equal to the piles, which means the last person, which means this person standing at the index I, he can take the entire stuff of the end. He will try to take the entire stuff and just return the stuff, sorry, which means taking the entire stuff from I up till the end. From I to end, we take the entire stuff. As simple as that. Now comes the actual main part. Because we have only two variables, which is I and m. These are only variables which are actually variable. So as we also know that we initialize our DP array, it is nothing but by I and by m. Now you will say, Aryan, it is m, but you have written it n. I, okay, we got it that it goes up till n, but see, your m also, it goes up till n only. Why? Because you remember this part, that your, even if no matter how hard you try, you have to stop right here. So your m, no matter how far it exceeds, if it is coming at this point, it would have been under the limit of I. That's the reason it would have been under the limit of n. So I have a simple DP initialized with n cross n, right? As simple as that. And simply I have the memoization part. If my DP of I comma m, simple memoization which we do, that okay, if this part is already not seen, just return that part. Now comes the interesting part. I need to find, okay, what is the result like? For sure I know I have to try for every of those x, which is from 2 to m. I'll just make it smaller a bit, and yep. Now I know, okay, my x is from 1 to 2 into m. So I just tried for every x. Now when I say every x, I know I am standing in the index I. So the sum I can have is the suffix of I. I can have the suffix of I as sum, but because then I can choose only the x elements. So after choosing the x elements, the next part which will go to the other person, he will try to maximize it. So he will try to maximize, which is the next person will try to maximize, because helper function gives the maximum value. Try to maximize by choosing the I plus, by starting from the I plus x element, which is by leaving the x elements from I, because x element have been grabbed by this person which was choosing that particular part. And then also I need to update the m, because m is dependent upon the x itself, that how much x you choose, and that's how you will get the new m. And that's how you will get the new ith location for the next person. And because he wants to maximize it, that's the same reason I just use the same helper function, because same helper function is actually maximizing that stuff. Now ultimately I will just get the maximum. And why maximum, Aryan? Because ultimately your result will go on and compute and choose all the x's and take the maximum out of all the x's. That's the reason ultimately I will just get the maximum, store it in the DP and return that answer. Now, simple complexity analysis, very simple. And also, if you just remember that part, I just explained that same stuff again, that if I'm starting to compute from here, so I need the suffix sum like this, so that I can just compute this sum and subtract this helper part right here. That's the reason I just computed the suffix sum, although you can actually have this as a sum from location I to I plus x, but it will again add a complexity of O of n plus O of n, which means it will actually make it more, which means earlier your complexity will be O of n square into n, but then because of this addition part, it will become n plus n, and if you do it more worse, it will become n into n. It is how you actually do a computation of a suffix sum. It depends upon that. I'll show you, but yeah, it is that because of finding this suffix sum at every point, I just did a computation already and use that suffix sum. Now comes the complexity. As simple as that, we saw that okay, it's a dp which is going on from I, basically the dp function, it will have a I cross m recursive calls, and for every recursive call I will go up to 2 into m. That is the reason I have n cross m as a recursive calls, and this is for every recursive call, a call which goes up till 2 into m, and we easily saw that m is bounded by n, thus it's the reason the complexity is O of n cube, and n is nothing but the pile's length. For sure you know that part. And for sure space is nothing but O of n cross m, although n is bounded by m is bounded by n, that's the reason space is also O of n square. Now the tabulation part, although it's not required, video is done, you can go, but the part of tabulation you can easily know. If you have made the recursive, then it's very easy. It's exactly the same, simply the exact same base case. I initialized my suffix sum because for sure I would be needing the suffix sum. Now the dp is initialized, as for sure dp would be initialized. Then I know I have to go at every I also know that I have to go at every m, as we saw in recursion. Then I also know that okay, what if I can take all the n elements if I am at I, then okay, I just know my x I can choose from 1 to 2 into m. If I, by just adding my maximum m, which is maximum x, which is 2 into m, if I can grab all the n elements, so I can just simply add that suffix from I. Else I can just simply and try to take for every x and see okay, what is my opponent score, what is my score. My score will be nothing but the suffix of I, as simple as that. As you saw, suffix of I, okay, where it is gone, this is part, okay, let me erase this pretty quickly. It is suffix of I, which is what I can have minus of what is opponent score, which is he will just also try to maximize this, and that is the reason he will just try to maximize his score, which is done by this. And you saw exactly same stuff will happen. Nothing but opponent score, if you just see, it is nothing but it is grabbing the value from I plus x index, and also grabbing maximum as x comma m, because m will update according to the new x being chosen. And that is how I will ultimately get my dp of I comma m, by choosing all the x's from 1 to 2 into m, and that is how you will get the answer, by simply grabbing the maximum. And ultimately I will just return the dp of 0 comma 1, and let's see, nothing got changed exactly. And I will highly recommend to do the memoization part and not this part, because no optimization here also is possible. So for sure it's good to do the memoization part, because it's easy to understand, easy to write, easy to explain, and easy to infer also. I repeat the same stuff again and again, but yeah, the time exactly same, space exactly same, and that is how you see. This is exactly same as recursive plus memoization, although it's hard to write this down initially, but if you just write this down, recursive thing which I showed you above, then it will be a cakewalk for you to write this code of tabulation if someone asks you to write, but it's of no use to write. Cool. The code of C++, Java and Python is down below. I have only written the memoization code, although you want, you can just grab the code of bottom from this particular video itself. It is here. Yeah, so goodbye, take care.